Today we're going to be talking about rotational dynamics. The word dynamics is different than statics. Statics means it's not moving. Dynamics, there's going to be motion. So we're going to be talking about things that are moving in a circular fashion or rotational. Okay, so we've talked about the last couple times that we had displacement, which is x, is equivalent to theta in rotational motion, and the velocity v is equivalent to omega when it's rotating, and the acceleration a is equivalent to alpha when it's rotating. But now, what about the force? So today we're going to be talking about what is the rotational equivalent to force. Well, that rotational equivalent is what we call torque, okay? And it has a Greek letter tau. It kind of looks like a T. We don't use T because T stands for tension when we're talking about ropes and blocks. So it's kind of like a curly top on here and a lowercase t at the bottom. It's called tau. And what we talk about when we're talking about a rotational force is kind of like if you're opening a door. So if this is an aerial view of a door, and this is the hinge that's attached to the wall over here, and here's the doorknob, and you push on the door, and the door is going to rotate around in this fashion this way. And it's going to rotate with an omega around in that way. And the angle that it rotates would be your theta. Well, the force that you push onto the door isn't going to cause it to rotate, or the force is going to cause it to rotate, and that force is going to be equivalent to the force times the length that it takes, and that's what's going to be happening. So it's going to be the rotational equivalent to a force. So think about some of the things that help you open a door. If you were to push right here where the hinge is and we're trying to open the door, it wouldn't work. So we know that the further out that you are from pushing on that door, it's easier to open the door. So if you go home and you try to push the door in the middle, it's not going to open as easily as if you push it on the outside. So the distance that that force is applied to the hinge makes it easier or harder to open or to make it move around in a circle. And now if you push this way on the door, it's not going to move at all. No matter how hard you push at F3, you can push straight down here, it's not going to move at all. So that's kind of what we're going to be studying right now. So let's get into more definition of torque. Okay, so torque is the quantity that measures the ability of a force to rotate an object about an axis. So as far as the door was concerned, the door hinge is the axis that it's going to be rotating about. And everything rotates about a center, and that's what we're going to be talking about, is what causes an object to be able to rotate. There's going to be a force applied that's going to cause it to rotate. Okay, there's a couple things that it depends upon. The torque depends on the force applied. So if you try to open a door with just a little push, it's going to be a lot harder than if you push it with all your force. If you have a large force, that torque is going to be larger. If you have a smaller force, the torque is going to be less. It also matters the length of what we call the lever arm. And that's what I meant. If you try to push the door, the further away you are from the hinge, the easier it is. That's what we call the lever arm. Okay, and we'll get into more of that tomorrow, but the lever arm is going to be the distance from the axis of rotation to the force. Now that lever arm, it's the perpendicular distance, and we'll get into that in the next slide. It's the perpendicular distance from the axis of rotation to the force. So the further away you are from the rotation point, the easier or the larger the torque is. It also matters the angle that the force is applied at. So if you try to push a door this way, it's going to be a lot harder than if you push it straight up and down. That's what we're talking about, perpendicular. So the best way to push a door would be perpendicular to the door, not at an angle like this. So this is the formula for torque. It's that tau, the funny looking T, is the force times the distance times sine of theta. And the theta is the angle from the force to the door, or the force to the line that goes through the axis of rotation, which we call the lever arm. So torque is equal to force times the lever arm. So here's a example, if you have a wrench, and a lot of times they're called a torque wrench, and the reason why is because you use torque to rotate. So you have a bolt here, and you want to pull on this wrench to unloosen or tighten the bolt. That's right here. So our axis of rotation is the center of the bolt, just like the axis of rotation of the door was the hinge. The distance, or the lever arm, is going to be the distance from the axis of rotation to the force, where the force is applied. So this is our D. The theta, once again, is the distance, or the angle from the force to this axis that goes through the axis of rotation. So this is your theta. Torque is force times distance times sine theta. Now torque is a vector quantity. That means it has a magnitude and a direction. The magnitude you just plug in here. Now the direction's a little bit different. Our direction, instead of left, right, up, or down, our direction now is going to be clockwise or counterclockwise. Now we tend to think that clockwise is a positive number, but in physics, clockwise, so if it rotates this way, the same way that a clock does, it's actually a negative number. And if it rotates counterclockwise, so this is our counterclockwise, it's positive torque, and this is clockwise. So this is something that you really have to make sure that you remember. Counterclockwise is